Brian Pailes. Currently, Brian is the principal engineer for Vector Corrosion Services in Tampa, Florida.
Good morning, and thank you for having me. So today I'm going to talk about non-destructive testing to better define repair quantities for reinforced concrete structures. A major issue facing all the owners here in the room and throughout the country is how do we properly define our repair quantities for construction and the repair. You know, sounding and visual inspection are tools that we commonly use throughout the industry, and they're very effective, but they're known to underestimate the true total quantity in the end. You know, underestimating these repair quantities can have kind of two major impacts on your project delivery. Mostly, first and most importantly, usually change orders can be costly. With the increased quantities, those costs increase. And then it can also delay your ultimate project delivery time. And then, you know, another factor that we have to consider too is when we go out and do these inspections, it can take maybe years or it can take a long time from when the actual project begins with the repair phase. So deterioration will definitely have grown from the last inspection. So how do we better understand how that growth is occurring so that we can actually, when we get to construction, have a better idea of what's going to be repaired? And then one thing I always kind of stress is, you know, we kind of get hung up on decks a lot when we talk about chain drag and repairs, but what I'm going to be talking about, any aspect of the reinforced concrete structure, you know, corrosion and deterioration happens on all the parts, so we can use these methods on any aspect. What's really happening in the concrete, you know, we go out to, so here we have a pier, we have a BMC, and we have a delamination, right? We've gone out and sounded, we see a delamination right there at the seat. And this delamination is found by hammer sounding. So clearly it's large, it's near surface, it's delaminated, debonded from the concrete. But there are other things happening in that concrete around that area as well. There's more delamination than what we found with hammer sounding. So hammer sounding can only find what the human ear hears when we hit it with a hammer. That delamination, that debonded concrete, may actually, and probably does, extend beyond that. So if we just tell the contractor to repair the area we hatched out, we're actually, when he starts chipping away, it's going to most likely grow. How do we better identify what that area is? And then beyond what is delaminated, even what we can't find with hammer sounding, there's probably some corrosion beyond that hasn't debonded the concrete yet. We haven't formed enough iron oxide to create enough cracking yet, but there's active corrosion potentially around there. So there's a lot of other activities happening around this delamination we found with hammer sounding. And if we just go out saying, oh, just repair that hammer sounded area, are we really addressing the total problem? And are we actually, when we start doing the work, is it going to grow significantly and we're going to have to pay a lot more money than we expected? How can we better understand these incipient deterioration conditions, as I call them, around the hammer sounded area? Concrete deterioration, and you know, obviously I'm a corrosion guy, so I kind of talk about it from a point of view from chloride exposure, and in the Northeast, that's obviously very important here. So with structure condition, you know, obviously we start with chloride and moisture penetration into concrete. Then from there, we start to get rebar corrosion. Iron oxide starts to form, and then that starts creating cracking, delamination, and then eventual spalling. You know, historically, we use chain drag visual inspection to survey our structures, which are important tools, and I'm not advocating not to use those. But what are we identifying with those tools, right? Where visual inspection is when we can see surface cracking or spalling, late stage in the deterioration phase. Chain drag or hammer sounding can only find those late stage delaminations that are audible in the human ear. So what about when there's just rebar corrosion or some of those early delamination phases or where chlorides are penetrating? How do we identify where those areas are? Tools like electrical resistivity, corrosion potential survey, which some people call half cell, can identify active corrosion. GPR is a very good tool that can identify a lot of different conditions. Impact echo can identify delaminations before hammer sounding and chain drag. So I'll kind of talk a little bit about each one of these things. Obviously with visual inspection, we want to find rust staining, cracks, spalls, exposed steel, things of this nature. You know, with hammer sounding, we're going out there, we're doing chain drag or hammer sounding, we're locating those near surface delaminations. Because what we're doing is we're hitting that concrete and it's creating an audible difference in the tone. And so we're assessing that because we can hear it. These delaminations are very large, near surface, and late in the progression. But before they get there, they exist, but we just can't hear them with our human ears. The nice thing about chain drag, though, that I always kind of say, you know, it's for a non-destructive testing method, it's interesting because its false positives are rare, right? If we hear a delamination, then a delamination exists. So it's a very effective tool. Like if you hear a delamination, you know you have to repair something. However, false negatives can be common, right? Just because we didn't hear something doesn't mean something doesn't exist. How do we better understand where those areas of delamination that haven't grown are? So the first thing that I'll get into is corrosion potential measurements, also known as half-cell measurements. This is covered ASTM C876. And this determines the probability of active corrosion in a reinforced concrete structure. And what we're doing here is we have a reference electrode, and we're measuring the potential of the reinforcing steel versus that reference electrode. So it's just the reference electrode connected to a multimeter and then connected to the reinforcing steel. And you can see this gentleman here, you can see there's been a delamination survey, and he's there to identify where is active corrosion beyond the physically damaged concrete today. So he'll make measurements maybe on a grid around that area to identify where active corrosion is. So if we go out on a bridge deck, we can do this on a bridge deck and go, say, for example, in this project, it was a 2x2 foot grid, survey the whole area. And we can identify, based on those kind of hot colors, where the probability of active corrosion is high. And so obviously this bridge actually is very late in its deterioration phase. It was about to be replaced. So you can see there's a lot of active corrosion on that. Well, how does that really compare to when we go out and do a sounding survey? So you can see I overlaid the hatched areas are a delamination survey. So if we just went out and did a delamination survey and we said, okay, those are the areas we need to repair today. Well, are we really addressing the problem today? Because if we have a bunch of active corrosion around those delaminations, well, those active corrosion spots are going to become delamination maybe in 3-5 years. So if we just repair the delaminations today, are we really addressing the ultimate problem of this structure? Are we making it last the long term? So if we do half cells with delamination survey, we can really understand, well, what do we have to do with regards to maintenance now so that we can preserve this bridge for a much longer period of time? So I don't have to come back in 5 years to do more work. And you can see, obviously, there are a lot of active areas outside beyond those chain dragged areas. And that's to be expected, right? Chain drag is a late stage deterioration mechanism. It's expected that there's active corrosion beyond that area. But it's also important to know we can do this not only on bridge decks, but also on substructure elements. So this is a structure, this is actually a railroad bridge over a local road in Missouri. And so they wanted to know, so you can kind of see that the road dips down below the bridge. And so there's a lot of water pooling and a lot of chlorides that get onto the piers in this bridge. So they wanted to know where the active corrosion was. So by doing a survey on a pier structure, we can identify where corrosion is active, and you can see there's a lot of hot colors at the lower elevation of those columns. And it's a little hard to see, but you should be able to see the hatched areas where the delaminations are. So there's some delaminations in those lower elevation of the columns, and then a lot of active corrosion. So we know we need to protect probably the bottom 4 or 5 feet of those columns. One interesting thing to kind of bring up about this is that the footer is not as active as the columns. And you would kind of expect that in this structure, why is the footer not getting as much active corrosion as the columns? It's closer to the roadway, potentially has more moisture and chloride exposure. This actually gets to a whole service life thing. The reason for it is that the cover depth on the footer was better than the cover depth on the columns. So the steel had more cover in the footer, so while the exposure condition was relatively similar or maybe even a little worse than the column, because the steel had a little bit better cover, those chlorides and moisture haven't reached the steel yet. So the columns have started to corrode first because they had inadequate cover. With regards to preservation, long durability of service life of structures, cover depth is a major impact on that. So here we can identify where the active corrosion is now, where do we need to protect these columns so that they last much longer. GPR is another tool we use kind of extensively out in the industry. What it is, we're doing an electromagnetic evaluation of a reinforced concrete structure. And this is really good at finding steel in concrete, and it's because the electrical properties of steel are much, much different than the electrical properties of concrete. And so here we have kind of an image of a GPR scan there on the bottom right. And you can see that the bright white little hyperbolas, the little bumps there, that's the reinforcing bars. We can get a lot of information from a GPR scan. One, we can get where the rebar are, the layout, the spacing, or if we're going to do some drilling, we can make sure we're not going to hit the steel. Cover depth, as I mentioned before, cover depth is important in concrete service life. As we all hope, we have good cover depth when we design it, and we try to have QA/QC when it's being placed, but obviously steel placement can vary, and so sometimes we get areas of shallow reinforcing, and so those can adversely affect the service life of our structure. So we can actually understand the in-place cover depth of reinforcing steel and concrete through GPR. But then we can also kind of do this qualitative condition assessment as well. You can see in this image down here on the right that there's the bright white hyperbolas, but then there's some areas of faded. Well, what's happening here? Well, the reflection of the GPR wave from that steel has weakened. And there's a lot of different reasons that can happen. If there's a lot of moisture and chlorides in the concrete there, that'll weaken that signal as it travels through that. If there's a lot of cracking and delamination, that can scatter the signal, cause reflections, weaken the ultimate reflection. So there's a lot of things that relate to deterioration that can attenuate that signal. Now, I always mention a word of caution here because people kind of ears perk up a little bit and they say, oh, delaminations affect GPR signal. Well, can you go out and do a delamination survey for me with GPR? Well, not exactly. Yes, the delamination will affect the GPR signal, but I can't tell you if that attenuation was a delamination or was it just chlorides and moisture in the concrete. There's a lot of factors that attenuate the signal. So to specify, oh, that attenuation is to one type of condition is not true, and it can't really, it's hard to do that. So it's a tool to use to identify areas of potential risk or with damage now, but it's an area of further investigation. I can't tell you if it's physically damaged today or maybe it's just going to be damaged in the future. It's an important thing to understand with the GPR attenuation or velocity surveys. Cover depth, I mentioned, GPR is really good at finding areas of low cover, and so we can identify where areas of potential deterioration are going to occur. And the reason for that, and I won't really belabor this equation, people usually glaze over a little bit when I show tough equations like this, but this is Fick's law of diffusion for chlorides into concrete. So this is the kind of the equation we use to model how chlorides are getting into concrete, causing the corrosion. And if I set this equation to time, when is my concrete going to start to corrode? If I set that to time, you see that x is squared. And so what you're getting, so this is squared, and so what that means is that the depth of my steel has an exponential impact on the service life of my structure. Cover depth is really important, so how can we use that to really address the durability of a structure and identify where problems are? So we can go out to structures and measure on different aspects of them. So for example, in this project, we're looking at the columns and pier caps, and we wanted to identify where areas of low cover would be and where that would potentially put the structure at risk for corrosion and deterioration earlier in its service life. So if we go and scan GPR on these columns, we can identify there were a few areas of very low cover and in certain areas. And so what we can do with this is then identify areas that need maybe a corrosion inhibitor or a coating in those areas. So we can do some preservation techniques there so that we prevent any early age deterioration in those elements. Doing that kind of amplitude survey that I indicated. I live in Florida, and in Florida we have the benefit of not having to have de-icing chemicals, so we don't generally have any deck problems, generally. Most of our problems are substructure by the water. However, I like this example here because it's a deck problem in Florida. And the reason being is this is in down in Naples, Florida, if you're familiar with that area. San Marco Island has kind of two bridges to it. It's an island. And so this is on the west coast of Florida, so the west side, so the beach is out on the left here, and you have a marina here, and then the mainland of Florida is on the right. And so people on the weekend, they bring their boats out, they go out fishing, and then they come back. And so what happens when they pull their boat out of the water? Everyone is supposed to wash your boat down, clean it. How many actual people do that? As not as many as we obviously would like. So what happens is they take their boat from the salt water out onto their trailer and then drive eastbound on this bridge. And so what was happening was they were getting deterioration on the deck due to chloride exposure from boats. You can see by doing the GPR attenuation survey on the deck that the eastbound lane down the center has a lot of attenuation, whereas the westbound and further and on the other side. And I'm really only showing the first couple of spans. This bridge is quite long, and once you reach the center peak and started to go down, the attenuation stopped because now the boat, all that bilge water moved to the front of the boat and it stopped leaking on the deck. So really they just had an issue on the eastbound before the midpoint of the bridge, all because of these boats. And so we can quantify that area, identify where the extent of that is, and so now the DOT, well actually this is owned by the county, this is a county bridge, so the county in this case understood now where they needed to focus their preservation techniques, and by applying doing some repair in this area. Now this attenuation does not mean this is all delaminated. There's areas of active corrosion in there, there's areas where just chloride and moisture exposure is high, and there's areas of delamination. We went out and also did a chain drag survey so they know where they need to fix concrete today, and then they're going to do some add an inhibitor or a sealer on this on these early spans so that they can kind of prevent the moisture permeation into the concrete here. So by understanding that with this GPR, they can better attune their preservation techniques here. what if we want to find delaminations earlier in the phase? Well, a lot of times we use a technique called impact echo. And really what impact echo is just a fancier chain drag, right? Chain drag, we're putting stress into the concrete and we're listening to the acoustic changes. But our human ears only have a certain range that they can hear. So, well, let's get just a better ear, right? So we just use sensors. So we make an impact on the structure and we monitor that stress wave and we measure the frequency of it with some sensor array. And so if we have a delamination, that will affect the bouncing of that wave and the frequency. And so from that, we can identify where the delaminations are. We can use this information to identify delaminations before they become big enough that we would identify them with chain drag. Moving on, so we've got delaminations, and then also, there's internal cracking, vertical cracking, and so the wave velocity through the concrete will be affected by internal cracking. So acoustic methods are really good at finding a cracking and voiding and things like that. And then the other nice thing about acoustic methods is that we can identify the in situ compressive strength of concrete because the wave velocity is affected by the strength of the concrete. So the faster a wave travels in concrete, the stronger, more densified we know it is. And so we can go out on a structure, locate delaminations, locate internal cracking, and then also give you an idea of the compressive strength of that concrete. And so, on decks, obviously, there are rolling devices out there that can be used. So these rolling devices will roll out onto a structure and identify delaminations and cracking. And effectively on this what I'm showing here, here's an array of sensors in along this route, and then there's also a trailing sensor in this device. And so with these three sensors in the front, you're measuring stress waves transversely across the deck and identifying longitudinal cracking and delaminations. And then the trailing sensor can identify transverse cracking in the deck. And so by scanning over the deck, we can identify where cracking, delaminations, and other items are, provide a more detailed assessment of a bridge deck. Whereas chain drag is only going to identify those late stage delaminations, and we're not going to catch everything. If we go out and do something like this method and scan, we can identify delaminations before they become those large. And so we can better identify those quantities. Because once we start hitting those delaminations with a chipping hammer, we all know they're going to grow and get bigger. So how do we identify how big those are going to get? So we can better understand the true quantity of delaminated concrete in a structure with a test like this. As I say before, not just decks, right? Substructure elements. This happens to be a tunnel section, and we're doing the impact echo on a handheld device and doing it up and down the walls, looking for deteriorated areas. And so here's the sensor array and a computer acquisition system. One person, myself, working and somebody just watching, as all work has to be done like that. What we're out there to find is where the deterioration in this wall is. And so we start with an area, and at joint 6, they went out and did a sounding, and they found a lot of delamination around the joint, not uncommon, and then a little bit of delaminated area here. And so then we went out and said, well, okay, where's that delamination? If I went out there and hit that with a chipping hammer, it's going to get bigger. So how much bigger? So if I did the impact echo, now the delamination have grown, right? This is actually connected down here, and there's a little bit more out here, okay? So there's some more delamination, but okay, so that's delaminated concrete. Is there any other weakened concrete as well? Because we're collecting the compressive strength of the concrete as well, we can identify that, okay, so this is where the concrete is debonded, but we're actually getting some cracking a little bit beyond it as well. So if I start hitting this this is some weakened concrete. I didn't put the scale here, but this is like 2,000 PSI concrete because of the cracking. So I can tell you that now, in reality, instead of just originally repairing this area, I'm going to have to go out and repair this area. So that's the quantity I'm going to be telling the contractor he needs to be chipping out and replacing. More than double the original area. So by better understanding that quantity, we can better identify the repair quantities and get a truly more long-lasting repair out of that area. Kind of the last method that I'll talk about today is just infrared thermography. Infrared thermography is something that's been used a lot more, and effectively it's using infrared cameras to identify where delaminations are. Delaminations have different thermal properties than the sound concrete because there's an air gap. It's a thinner section. So that delamination, because it's bound by air, it's thinner. In the morning sun, it heats up faster. and in the cooling day, it cools down faster. And so because of that, we can use infrared cameras to identify that quickly. And it's important to note that those results are going to be similar to chain drag. Impact echo is a little bit more detailed and can find earlier stage delaminations than, say, chain drag can. And so IR camera is going to give you a little bit similar results to chain drag, just to be aware. But because it's fast, it can provide some benefits there. This is kind of, an IR camera here, and this is kind of an example of a time lapse on a dam face, which, can be a wall of concrete anywhere. And I've highlighted kind of two areas. And in the morning sun, they just kind of look like any other area. But as you see, as the day goes, you get this hot spot right there and right there. And so clearly there's a delamination occur. You can see that delamination as the sun warms that face. And recently we did this on a bridge in Minneapolis. This was actually a few years ago. The reason we did the IR on this structure was they'd gone out and done a complete hammer sounding a few years back, and then they were getting ready to start putting some contract documents out. Well, they'd known that so many years had passed between they had done the sounding and when they were going to put the contract out that, okay, most likely some delaminations have grown, but we don't want to resound this whole structure because it was a really large arch bridge with a lot of area. And so what we did was, well, let's just go do IR and shoot the areas we know had the delaminations before, and let's see if they've gotten any bigger and how much. And so we can kind of get a factor on those delaminations. And so by going out and shooting it with the IR, we already knew where most of the delaminations were. We could really just there to look to see how much bigger have they gotten over the last 3 years or so that we can kind of adjust our repair quantities. And so it was a really effective tool in that method because we're there to just kind of, confirm and correct hammer sounding in a very rapid way because they didn't want to spend a lot of money. Open it up to any questions.
One of the questions, we're a membrane and asphalt state, so a lot of the stuff doesn't seem to work on membrane and asphalt. So I've got kind of two questions. One is, what is the best method for membrane and asphalt state? And the other is that we had some half-cell potential readings done on a concrete rigid frame, and we've never been out there for maintenance, and it was showing red the entire location. And we said, we can't believe this. So we went out and actually did some test holes to see what was going on. The rebar didn't look like it was black bar. It didn't look any worse than the day it was put in. It was solid. It was, and it was exactly a spot where they'd taken a half-cell reading. And since we're membrane and asphalt, it still made sense to go back and actually go through and put another membrane over the top of it and get some additional life out of it where we're keeping the water out.
Address your second question first, and a clarification. So on that structure, was there originally a membrane and waterproofing on top or something, or was it just a bare concrete originally? Did they do it on top of the membrane, or did you actually remove it and do the half cell? So the problem that I'm alluding to here is, so half cell, if you're not, ASTM C876 has a guideline for the threshold values, but that is really only for atmospheric bare concrete. And so in your situation, you're going to have some oxygen deprivation, or when there's lower oxygen, it'll move all the potentials really negative. And if you don't truly understand how the corrosion potentials are working and you don't correct for that information, so actually the perfect example is one I showed. Before I corrected this data, the actual potentials on this footer were extremely negative. And it was just because there was a high moisture content, but there wasn't active corrosion. So if you're not properly adjusting for moisture and oxygen content factors that affect it, you can get confusing results. And that happens quite a bit, especially on structures that either have coatings and are drier and less oxygen, or extremely wet, like when they're not kind of atmospherically exposed. It'll shift the potentials one way or another, and you can kind of misdiagnose things. And so I've kind of gotten, actually, the last, at the Western Bridge Preservation meeting, I got kind of a similar question that someone wasn't trusting half cells. And again, we were kind of talking, and it was, I think a lot of people are going out and doing them when the situations are normal, it works great, but they get into these kind of unique situations and maybe just the expertise wasn't there to kind of verify. And so you have to be careful on those situations, and so that tends to what happens. So you have to be careful. If you get really negative numbers, but they're very constant negative numbers, that's usually an indication either the moisture content's high or the oxygen level's down, and that's actually not an indication of corrosion. So it's just kind of being careful. And then to your point about overlays and stuff, what methods are good for that? GPR has been relatively effective in overlays depending on the thickness and things like that. However, if you're trapping moisture in your pavement in an area, that'll really affect the attenuation of the GPR. So you might actually have had an issue just with water in your pavement and not the concrete below. Impact echo, when your bridge deck is frozen and it's hard, then usually that'll work through the pavement. But if it's a warm, sunny day in July, the pavement is, has some give to it. It's soft. So impact echo and acoustic methods like that won't work. But when it's frozen solid in December, actually we've seen decent results with impact echo when it's hard. But I would say your best bet is GPR as kind of an initial tool, but the pavement is going to affect it quite a bit, especially depending on moisture and drainage. And so you can't, you'll have to then say, okay, these are potential areas, but we need to look further at them. But it does kind of limit your abilities.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.